Hi everyone, welcome to activity 5.8. So this is a continuation of 5.7, talking about radical equations. Our goal really in this activity is to be able to not only, if we have an equation like this up here that we're starting with, very similar to what we started with in activity 5.7, we know we can plug in a value for d, take the square root, we can evaluate and find t, but our main goal is to be able to plug in a time and then solve for d. So that's where this solving radical equations comes in. So they're giving us this model for an object that's dropped from a tall building, okay, very similar to 5.7. They're saying that t equals 1/4 square root of d. Okay, so this is really the inverse, okay, of this is a square root equation. It's the inverse of a square equation, and that will come up again after. So the first thing I did, we had to fill in this table, just plugging in these certain values for d. See, we're very comfortable doing this. It's more of what happens when we want to plug in a t. Okay, so I plugged in all those values for d and got my corresponding times, and then I graphed it. I sketched it below. So take a few minutes and do that part. And then you can see that this graph does look like a square root graph. It's kind of like a half of a sideways parabola. A parabola is from an x squared. Okay, so that graph, we're going to use that graph to now do part D. So how tall must a building be for an object to take 6 seconds to fall to the ground? So my graph might not be perfect. I started plotting a few points and then I just sketched it after that. But I would say for the time to be 6 minutes, if we go over here on our graph, somewhere over here, I'm just looking over here, between 500 and 600 feet tall. Okay, that's just an estimation. We will find that exact value in a little bit. Okay, so that's what we're going to do next. So these are radical equations. So let me focus this video more on the actual solving radical equations and not as much on the applications, because you've done just so many applications at this point. So they're going to start you off with a couple examples. This part right here that they're giving us, this property right here, is really just saying that if two exponents are the same, then the bases must be the same, and vice versa. Okay, so I don't really use that fact directly when I'm solving these equations, but let's take a look at this example they have here. So that one they're stepping you through, and basically they're showing you that if you have something like this, I always want you to think of what you can do to undo what's happening. So if I have a square root and I have to get to that s, my first thing I'm going to do is I'm going to square both sides. Okay, because a square and a square root undo each other, and that gets me my s by itself, and I get s equals t squared. So it's not a coincidence that I got a t squared equation, because a square and a square root are inverses of each other. They're having you take this step, which you definitely can do, of remember the square root of s is the same thing as s to the 1/2. They're exact same things. Okay, it's just writing it a different way. And the one thing that can make that useful, make it more useful when you're solving, is you can see why I get plain old s when I square both sides. Because if I turn around and now, let me rewrite this for a second. Okay, let's say I was back at the beginning here. Okay, and I wrote this as s to the 1/2. Well, then when I square both sides, you can kind of see why a square root and a square undo each other, because I multiply these exponents and I get plain old s. Okay, so I got the same thing. I don't have to rewrite it like that power, but it is useful. So now we're going to take another example down here. Okay, same kind of thing, but it just has that divided by 4. So there's multiple ways I can do this. I am going to always work on getting the radical, this radical by itself, before I do anything else. So I'm going to multiply over that 4 and write it like this. Okay, and then I'm ready to square both sides. I'm going to undo the square root so I can get into that d. Keep in mind I have to square that whole part, that 4t, so I end up with 16t squared equals d. Okay, so that equation is just solved for a different variable. Okay, so I could use that formula now, use that new formula to determine how tall a building must be for an object to take 6 seconds. So now I can use this and get my actual D here. So D would be, if you do that calculation, you end up getting 576 feet. So our graph was not terrible, not exact. We said between 500 and 600 feet tall before. How does your answer compare? It's about the same, we'll say. Okay, so you can also do your part. So what we did in 2A is we first solved it for D and then plugged in a time. What we're going to do right here is we're first going to plug in the time. See, they plugged it in. They plugged that 6 in for T right away, and then solve it from there. Doesn't matter which way we do it. Okay, either way I'm going to multiply, so I'm just going to put an arrow here because I'm going to make this 24 equals square root of D. Okay, and if I square both sides at this point, I get D to be same thing. All right, so I'm going to let you, so the example 3, they're going to step you through. I would rather use the video to, I'll let you look through examples with the work, with me showing the work through. So I'm actually going to, so there's the rest of example 3. And if we move up, I'm going to skip this part of the number 3. I'm going to skip. Okay. We'll get enough practice in on the next page with doing a couple examples, and I'll have another short video with another example. So I'm actually going to flip over and then go to number 5. Okay, so 5, I would like to do along with you. So I'm just going to scribble this out. I want to just pretend like we're looking at it without any work, and I want to do it with you. Okay, so my goal in doing these is to, I know I'm going to have to square both sides. That's the only way I'm going to get into that x so I can get x by itself. Okay, but I can't do anything right now. I don't want to square too early. I want to wait until I want to get this part alone first. So that's what I'm going to do. So I'm going to bring over that 5. Okay, now that I have my square root part of the equation by itself, now I'm going to square both sides. Okay, so once a square and a square root will undo each other, they're inverses, so then I will just get x plus 3 equals 25. And I'll bring over that 3. Now I have a nice linear equation, and I get a 22. So the solving part's not too bad. Now, on this one, we started off with a radical equation, and if you look at where I was right here, I ended up making that radical equation into a linear equation, and it definitely helps me solve, but the problem is that sometimes I get extra answers. Okay, I always find all my answers, but sometimes I get more answers than I should, and those are called extraneous. So we have our solution, so this would be for part A right here. So this value, we solved it, so that would go right there. So the next part is telling me to check this. So watch what happens if I check this 22. Okay, so under here I get a 25 plus 5 equals 0. So I have 5 plus 5 equals 0. So a lot of times people say, well, if it was 5 minus 5, it would work, so it looks like it checks. But it doesn't. Okay, this is not a true statement. So this is an example of what we call an extraneous solution. Okay, I made this radical equation into linear, and I got a solution, but it does not work in the original. Okay, so what ends up happening is this one does not check. X equals 22 does not check, does not work. Okay, so 22 is an extraneous solution. So I always have to check for extraneous solutions when I'm solving radical equations because of what I end up doing to the equation. So if I had any other answer, sometimes I get 2 answers out of these and maybe one's extraneous, one's not, or maybe they both work. We don't really know exactly how many answers when we start. So if you go and try to graph this one, you'll find that this graph right here, you can sketch it on your calculator, but it's going to end up being a square root graph that is shifted actually left 3, up 5. It's going to look like this. which kind of makes sense with what we just said because it doesn't have any intercepts, or it doesn't have any x-intercepts, so no x-intercepts, which is why this one had no solutions, because I was trying to find the x-intercepts up above. Okay, so let's look at number 6 and do one of these with some decimals in here. So they're giving us a table for the years since 2001 and the number of undergraduates receiving loans. Okay, so they're giving us the actual model right here. So all we really have to do is use that. We could do regression on that table and get that function, but they gave it to us. So determine the year that this model would predict that the number of undergraduates is approximately 8 million. So everything's in millions. So all I really need to do here is plug in an 8 for my n of x. And you see this fits in here because I'm trying to find x, so I'm eventually going to have to get that radical off. But my main goal first is to get my radical alone. Okay, so I've got to do a whole bunch of stuff first. The first thing I'm going to do is I'm going to bring over this 3. So it's gone there, and I end up getting 4.558. And still I'm going to try to get the radical more alone before I square both sides. I'm going to divide out that coefficient. So I end up getting, I think some textbooks, and you may even see with this one, end up doing all this in one step. So they leave it like this. You can divide it out now, but this textbook, just so I follow it, leaves it like that. Okay, and then I'm trying to get the square root off, so I'm going to square both sides. And does it all in one step. So I have x plus 0.24 equals this value over here. In the end, I end up getting 13 point, oh, let me just get rid of this one thing. So after I subtract that over and everything there, I end up getting a 13.7. Okay, that's doing all this arithmetic out on the left side and bringing over that 2.4. Okay, so that's how many years after 2001 that the school would have about 8 million people getting Stafford loans. Okay, so you've got a summary here, which kind of goes through the steps of how you're trying to isolate the radical and square both sides. I am going to take a couple examples from this page that are below, and I'm going to do them in a separate video just so you have a nice short video of just solving radical equations.